In this video, we're going to be looking at the integral test. And up to this point, we've talked about the nth term test for divergence and geometric series. And the class of series that those tests are applicable to is relatively narrow. So I think that this integral test is actually, kind of what you've been looking for. Something that can tell us if a series converges or diverges with certainty. So the way it goes is it says that we can determine the convergence or divergence of a series based on examining the corresponding improper integral. Okay, and that's a big deal. Now we do need to first verify that the terms of the sequence are modeled by a continuous positive and decreasing function, and in AP Calculus that's conditions that we're going to need to check anytime we use the integral test. And in this video, I will not be proving that theorem, but if you're interested, I have done that in a separate video, and you could click up at the top, and there's a link up there that would take you to that video. All right, so the first example is we're going to show that the harmonic series diverges using the integral test. And in case I haven't told you what the harmonic series is yet, that's just 1 plus a half plus a third plus a fourth and a fifth and a sixth and a seventh and an eighth, all the way, forever. Okay, that's the harmonic series, and it diverges, and that's a fact that we're going to be able to, just kind of recite without proof in the long run, but for now I'm going to give you a reason to believe me why that's true. So, wrote it like that. We could write it in summation notation as the sum from 1 to infinity of 1 over n, and if we're going to do the integral test, we need to think about the corresponding integral. Okay, and it's not hard. Okay, the bounds of integration are the limits of the series. Okay, and the integrand is the summand, right? So it's just going to be 1 over x dx. If you wanted to, you could integrate 1 over n dn, but I'm just going to do 1 over x. Okay, so this is an improper integral, and remember we know how to justify our answer in an improper integral situation, but before we even use the integral test, we have to check those conditions that are with the highlighter up at the top. So we're going to point out that on the interval 1 to infinity, 1 over x is a continuous positive and decreasing function, and I will take the second right now to tell you that if you're asked to use the integral test in AP Calculus, the conditions are going to be met. I'm not going to ask you to do the integral test on something you can't do it on, but we do need to write those out every time. So 1 over x is continuous positive and decreasing on the interval 1 to infinity. Okay, now I'm going to go over here and start in on the improper integral. Remember, there needs to be two limits. One needs to be the limit of an integral. Okay, so the limit as b approaches infinity of the integral of 1 over x from 1 to b. And then we go off to the side and we do our scratch work. Okay, to figure out what's going to go in on the inside of the next limit. So we're just going to integrate from 1 to b 1 over x dx. We're going to anti-differentiate, get natural log of the absolute value of x. We're going to plug in b, and we're going to plug in 1 and subtract. And we're going to remember that natural log of 1 is 0. So that's just going to be the natural log of b. And that's what's going to go on the inside of my limit. So I go over here and write out that limit. And as b approaches infinity, the natural log of b is also going to approach infinity. So I'm going to say this limit doesn't exist. And the fact that this limit doesn't exist means the integral diverges, the series diverges. And that's how the integral test works. All right, now that's pretty much it, how it goes with the integral test. And as far as us needing to use it in this class, we'll do some more examples, but the only other thing I need to tell you about the integral test is this related fact. If the integral and the series both converge, then the series is greater than the integral. Okay, and the equal to is only in like a really, really fringe case. I think where there's a lot of zero terms. So what I'm going to do is I'm going to give you reason to believe why this might be true, not exactly prove it, but I'm going to just draw a picture of what just happened, what we did. We thought about the graph of y equals 1 over x, and we took the integral of 1 over x from 1 to infinity. So we took that area, and we found that that area was itself infinite. Okay, so that amount of area approached to infinity. And what I'm actually interested in is the sum, the harmonic series, the sum from 1 to infinity of 1 over n, which is 1 plus a half plus a third plus a fourth and so on. So what I'm going to do is kind of compare directly on the graph. I'm going to say, all right, well, 1, that's kind of like the height of the graph right here at x equals 1. 1/2 is the height of the graph right here. And it wouldn't really make sense to compare, heights to areas. It wouldn't make sense. But if we gave all of these heights a width of 1 and turn them into a rectangle, then maybe it would make sense for us to compare areas. Okay? And you can see pretty clearly from my drawing that the sum which is represented by the, areas of the red rectangles, is going to be greater than the integral. Okay, so that's all I was trying to say there, was that the series is greater than the corresponding integral. And that's also kind of a hint at like the ideas of comparison that we're going to get at in the next lesson. I feel like I had something else to say about this. Oh yes, and if this looks familiar, like, hey, we've drawn diagrams like that in this class. We have, okay, when we did Riemann sums, and so that should also make sense that like this sum is equivalent to a left Riemann sum approximation for the improper integral. And if we're integrating on a continuous positive and, most importantly, decreasing function with a left Riemann sum, we're going to get an overestimate, which would show us that the sum was greater than the integral. All right, all that to say, when they ask that question in multiple choice, it's usually not that hard. Okay, so here's a pretty solid example. If the integral from 2 to infinity of f of t is 8 and an is f of n, what can we say about the series? Well, we know the integral test says... Okay, there we go. Now, I think if this was a real multiple choice question, not just one I typed up for the notes, it probably would have said if f of t is a continuous positive and decreasing function. And that does happen sometimes. And when they use those words, you know you're about to do the integral test, or at least be asked about it. Okay, and then we know that it's not equal to the value of the integral. We know that the series is greater. So that's going to be answer choice D. So let's execute this one a couple of times and then move on to the p-series test. All right, so the first one, a 1 over n squared is n runs from 1 to infinity. These are the type of the series, at least A and B, that we're going to want to use the p-series test on in the long run, but we've got to verify, the way that works first using the integral test. And so that's what we're going to do. So we're going to think about the corresponding integral, which would be the integral from 1 to infinity of 1 over x squared dx. But, that doesn't really get us anything. We're going to need those limit statements. So I'm just going to kind of be thinking that's what I'm going to do. I'm going to start off by checking my conditions. So 1 over x squared is going to be a continuous positive and decreasing function for x on the interval 1 to infinity. Okay, and I'm going to set up my improper integral. That'll be the limit of the integral of 1 over x squared as the upper bound approaches infinity. I'm going to go off to the side, set up my scratch work, integrate from 1 to b on x to the negative 2. I'm going to anti-differentiate, add 1 to the power, divide by the new power, plug in the bounds, and subtract. Maybe also think about that as negative 1 over x. Yeah, okay, when we did those improper integrals, that was really helpful for us, that rewriting. And then the negative 1 over b minus negative 1 over 1, that's going to be negative 1 over b plus 1. That's what'll go into my limit. And I'll think as b approaches infinity, okay, that fraction is going to go 0 plus 1, that limit's going to be 1. And because that limit exists, I know that series A converges. And specifically, I can say that A converges to a value greater than 1, okay, because the series is greater than the integral. But I don't know really a whole lot more than that. All right, now B, the sum from 4 to infinity of 1 over the square root of n. I want you to try that one on your own. Okay, so you should try to carry that all out with a video pause, and I'm going to bring in the answers here in just a few seconds. All right, there we go. So I've got kind of the same setup. The work looks almost identical, but just kind of something that happened with the anti-differentiation left me in a position where my limit didn't exist, which caused the series to diverge. So B diverges, A converges. And then C is going to be a little bit different, but I think I'm going to get the work for A and B out of the way first. All right, now this one's a little bit trickier. We're going to need to use a U substitution, but at the end of the day, it's just another integral test problem. So 1 over x log x from 2 to infinity, that's the integral we have to compute. So first we point out that f of x equals 1 over x log x is continuous positive and decreasing on the interval 2 to infinity. And then we're going to be interested in this improper integral. And so we're going to write this as the limit of a definite integral. And I'm just going to write it as 1 over log x times 1 over x dx to just kind of hint at the U substitution that I'm going to be doing. I'm going to go off to the side, and I'm just going to use the scratch work here for the anti-differentiation. I don't want to make any linkage errors or anything, so I'm just going to go off and say, all right, well, I'm just going to say U equals log x, which makes du 1 over x dx. Get that in the shot. Yeah. And then I'm going to substitute on the antiderivative at least, so I'll be taking the antiderivative of 1 over u, times du. And I know how to anti-differentiate that. That's going to be natural log of the absolute value of u. And this is weird, but I'm going to plug u back in, and I'm going to get natural log of the natural log of x, or at least the absolute value of natural log x. And it's an interesting function, but that's going to be what kind of populates the next limit over here on the left side of my real work. So I'm going to have a difference of two things, right? I'm going to plug in b, and I'm going to plug in 2, and I'm going to subtract them. Okay, so I'm just going to plug in b to that expression, to that antiderivative, and then I'm going to plug in 2 to that expression, and then I'm going to think about that limit. Okay, we know that the log of b does not exist as b approaches infinity. So, that log of b is itself approaching infinity on the inside of the absolute value, and we're again taking log of something that's going close to infinity. That's again going to infinity. This limit does not exist, so I can say that c diverges. Okay. Now this one is the type of series that I would say it's not like super common, like the harmonic or anything, but it does come up often enough in multiple choice questions that's worth just like doing once on the integral test, and maybe actually remembering that 1 over n log n, n to the first and log n to the first power in the denominator, that one's going to diverge. And maybe you've heard me in class give it a name. I've in certain years called this one Larry, and Larry diverges. All right, so we've done some integral test examples. I've shown you what the deal is with it. I think at this point you just need to go forward and practice. So that's going to be all for this video. In the same lesson in my class, we are going to do the p-series test, so you should move on to that one at this point. But thanks for watching.